Okay, good day to everyone. Today we're going to discuss another part of uniform rectilinear motion, and we'll be focusing on free falling bodies. So before we go over with some example of free falling body, let us review again what is free falling body from what we have learned from physics and from what we have discussed already in the previous lectures. So free falling body basically will be moving along your verticals, and the equations will more likely be the same as our uniformly accelerated rectilinear motion. So for our equations, what will only happen is that our acceleration now will be in terms of g, and our displacement will be in terms of y. But the equations will still be the same. So we have our three general equations that we could use for free falling bodies, that is v equal to v sub o plus gt, y equals to y sub o plus v sub o times t plus 1 half gt squared, and we have v squared is equal to v sub o squared plus 2g times the change in your displacement or in your positions. So for the value of g, or your gravitational acceleration, that is always now in negative value. So whatever the direction of your object under free falling body, the g will always be negative. And for the values of g, that will now be for the metric, that's equal to negative 9.81 meters per second squared. And for the English system, that will be equivalent to negative 32.2 feet per second squared. So for some computations, for the metric system, we can use a simple negative 9.8, and for the English, we could use a negative 32. But for us to be consistent with our computations, we will be using what is given in this discussion. So for our sign conventions, so we can use this diagram. So again, for your velocity, all objects or bodies that will be moving upwards will be positive velocities, and those objects moving downwards or towards the ground will have a negative velocity. And take note, whenever the object will reach its maximum point, its velocity now will be equivalent to 0. For your displacement, whenever our displacement or position is above the initial point, will have a positive sign, and if the object now or the position we want to compute is below your initial point, then it will be in negative value. So if I will have my initial point at this point, then all of my y now or my displacement are all positive values. So pag dito sa starting point natin is here, then I will have both positive and negative values of y. So kung kukunin ko yung positions, displacement from this point, the maximum height, then all of my y's will all be negative values. Okay? So to understand again and remember how to solve free falling bodies, let us solve an example. So let's say we have two rockets or launch at fireworks display. Rocket A is launched with an initial velocity of 100 meters per second, and rocket B is launched at t1 seconds later with the same initial velocity. So the rockets are timed to explode simultaneously at a height of 300 meters as A is falling and B is rising. So we can now understand the problem based from this diagram. So, si VA muna, rocket A will start first to move up. And once it reaches a height of 300, when it goes down, then that's the same time that VB is also moving up at the same height of 300 meters. But technically, rocket B will start later compared to rocket A. So in this situation, we are now going to solve for letter A, the time t1, and B, the velocity of B or rocket B relative to rocket A at the time of explosion. So, with this, so to solve for letter A, the time T1, which is the time that B will be released or be launched. Okay, so we'll now define our origin as the ground level. So YO is at 0. And we'll be using the equation y is equal to y sub o plus v sub o y plus 1/2 at squared or gt squared. So let's start first with rocket A. So for rocket A, YO is 0. Its final position upon explosion is 300. We are given its VO at 100 meters per second and G is constant. So substituting those values, we'll have this equation. Then simplifying it, we'll now arrive at a quadratic formula or quadratic equation. So by quadratic formula, we'll now be able to solve for the two values of time, which is 16.732 seconds and 3.655 seconds. So we have two positive times. So which of the two are we going to use? So the 3.655 seconds will simply be the time that E reaches 300 first, and then it travels upwards and down, and again reaching a height of 300 meters from the ground. This will now be your 16.732. So, kailan siya sasabog, mag-explode? That is at time 16.732. So, what will govern is our first value. Okay, so that's for the time of A. So, next, let us move to rocket B. So, for rocket B, we'll be applying the same equation. So, same, y sub O is 0. Final position is 300. VO is also equivalent to 100. But the time now that it will be, or that it will explode will be equivalent to T minus T1. Okay? So, with that, we have solved for T already. So, substitute 16.732 in the equation. And then we'll arrive at 4.905 times 16.732 minus T1 squared minus 100 times T minus T1 plus 300. Okay, so we'll now arrive at T minus T1, which is 3.655 seconds, or T1 now is equivalent to 13.077 seconds. So, big sabihin, after 13.077 seconds, nung na-release si or na-launch yung rocket A, saka pa lang marirelease ang rocket B. So, that's for T1. Or basically, since they have the same speeds or velocities, initial velocity, and they will be exploding at the same height, the travel time of rocket B to the explosion point is 3.655. So, compute mo lang yung difference doon sa kanilang travel time, yung travel time ni rocket A minus travel time ni rocket B, that will now be equivalent to this value. Okay, let's solve for the next. Okay, so let's solve the next part, B, which is the relative speed of B with respect to A. So as we have discussed in the previous discussion, the relative speed is simply equal to VB minus VA. So for our solution, we have to first solve for the individual speeds of rocket A and rocket B upon explosion. So we'll be using the equation V squared is equal to V sub O squared plus 2G times the change in your position. So let's start again for rocket A. So we know already your initial speed or velocity, we know your change in positions. G is constant. We solve now or directly substitute those values. So the final speed of A upon reaching the explosion point will now be computed as 64.14 meters per second. And it is a downward direction. And for rocket B, so just substitute our initial speed for rocket B and its change in positions. So that will now be VB is equal to, or squared is equal to 100 squared plus 2 times negative 9.81 times 300, giving us a value of 64.140 meters per second. And its direction is towards or upwards. Okay, so downwards is negative, upwards is positive. So we'll just apply the sign conventions in our computation. So VB A is equal now to 64.140 minus negative 64.140, giving us the relative velocity of B with respect to A is 128.28 meters per second, and its direction is upwards. So it means that as you observe from point A, B is moving upwards. So that's one example for free falling motion. So if you want more examples, there you can read your modules. We have several examples for free fall. Okay, again, for your evaluate activities, just answer the elaborate questions found in your module 1 unit